Welcome to the Melbourne MLAI Book Club. Today we're having an introductory session on reinforcement learning. My name is Eike, I work for ELISA, and my colleague Graham also works for ELISA, and my colleague Ruben also does. ELISA is wonderful to work for, and we're hiring. So if you're interested in the sort of thing that we'll be talking about during this presentation, have a chat with us, and yeah, we can talk about this a bit more after the presentation. So to start with, I'll tell you what I'm going to tell you. So let's start with what's reinforcement learning to begin with, because some of you have done machine learning already, and you've probably seen things like supervised learning, unsupervised learning, and so on. And I'll be covering the basic differences between reinforcement learning and supervised and unsupervised learning. We go through some fundamentals. What does it mean to do RL? What do we need to do RL? And in order to, measure how good or bad your algorithm is, you need some metrics. So talk a bit about that, and then we'll really scratch the surface of the algorithms. Also, I just forgot before we get really started, I do want to do the acknowledgement of country. I'd like to begin by acknowledging the traditional owners of the land on which we meet today. I would also like to pay my respects to elders past, present, and emerging. And that did not work out well, did it? Seems to indicate to me that we maybe should put that sticker somewhere else, or I need a smaller laptop. Come on, come back. There we go. Okay. To start off with, what's RL? You've probably heard of supervised learning and unsupervised learning, and in those, either the answers are known or the data is known. The output for a supervised learning algorithm is predetermined. You want the machine to replicate kind of what you know, whether it is what a cat is or a dog is, or any other kind of regression problem that you might have with a supervised learning algorithm where you want to approximate some kind of function. And our neural networks do this really well, but that is not really what we're doing in reinforcement learning. In unsupervised learning, the output itself is not determined. You want to find structure in your data, but that is also not what we're doing with reinforcement learning. It's not reinforcing anything. In reinforcement learning, what we know is the actions that you can take. The environment might not be known, the environment in which we are taking these actions. So the output, just like with unsupervised learning, is not determined, but the answers are not known in a way that you could tell beforehand what you have to do. So reinforcement learning is decision engineering. Yeah? If we think of supervised learning, you have a regression problem like this, and you try to find the best approximation to what to do. To how to distinguish these two. That is, not, of course, not what to do. That is how to understand the data. And if you look at unsupervised learning, you find structures in data where here, this is the famous iris data set, and the yellow points represent the centroids of these groups of types of plant. And the thing that most people think of when they think of reinforcement learning is some kind of robot that moves around. The cool thing about reinforcement learning is there's actually a lot more than that. And in a way, people think about it as training the same way that you would train a dog. But I'm going to argue that it's more like growing a plant. And I hope that you'll see afterwards why that is the case. So, what do we need to know to decide what to do? Well, the first thing that we need to know is who does the doing, like what is the agent that we're using for our reinforcement learning algorithm. Yeah? This agent can have multiple forms. It could be that the agent is a Roomba. It could be that the agent is a robot, but it could be that the agent is a building. It could be that the agent is anything that has to schedule, say, server loads. Yeah? Anything that has to make a decision can be an agent. And the decision can be something like, it could, in principle, be a digitally controlled light switch. The decision could just be turn the lights on or turn the lights off. The second thing that you need to know is where this all happens. Yeah? You want to know what your environment is. I'll talk a bit more about the environment. I've got some interactive slides for you there. But in principle, anything that you can be in and can make a decision in is an environment. And the third thing that you need to know is, of course, like what the effect is of your actions. Like you do something, and you want to somehow measure the result of what happened. So when you switch the light on and off and nothing happens, there's no reaction to you being the light switch, then how should you learn when to switch the light on or off? As simple as an action as that might be, similar to our classifier that distinguishes between dogs and cats, if you don't have any feedback, if there's no way for you to know which to prefer, then you can't make that decision. So you need to know what happens. Okay, so here comes first interactive part. So what do you think qualifies as an agent? What do you think is required? So does this guy qualify as an agent? Okay. Why do you think that person qualifies? That's a bit of a circular argument, don't you think? What? A rational way of making decisions. That sounds interesting. Could you grab the microphone over there and tell me more about that? You might have to switch it on. The switch is at the front.
I would say the agent probably needs some sort of function or algorithm to determine the best answer.
Mm-hmm. Okay, so answer in what way? What do you mean? Because you could have, like this robot could be something that welds a car door to the car, right? And so the only answer that it might need is there a human in the way? And every time there is a human in the way, it moves fast. No, it wouldn't move faster. It would just not weld the door to the car. Yeah.
Like if it's able to see some sort of probability that something is, that it's able to recognize that something has a greater probability than another one, or has a higher ranking than something else.
A higher ranking than something else. That sounds interesting. What do you mean by that? Or can you give an example? Like,
so if there's if you know, there's 5 different foods in front of the agent, and the agent knows that, you know, the agent is able to rank the healthiness of those foods some way. Mm-hmm. It's able to pick the best one from that ranking system. So it's able to make that decision, the first one.
That sounds kind of cool, but that sounds like something I could in theory do with an app on my phone. So I could have a classifier and an object detector on my phone, and I hold this against like these 5 fruit, and it says one of them is made of wax, the other one's made of plastic, that's marzipan, and these 2 are real fruit, and take the apple or the carrot, kind of thing. Yeah? How do you think the decision should come in there? Like, what's the reinforcement part about it? What's the learning part about it?
Well, if the agent eats a certain food and can see that it's making it, it's healthier, or it's able to make the same decision the next time.
That's it. Yeah, that's interesting. Okay, so what about this guy? And feel free to pass that microphone to someone else, or for someone else to volunteer to give an answer. Does that qualify as an agent? Because similar to the robot in the first example, it could just do something. Like, what was
the broom can't do anything by itself.
Ah, okay. Could you pass the microphone on to him, please?
Oh. Yeah. Okay, well, so what I thought an agent is just someone who can take actions. Mm-hmm. That was
right.
What I would say.
Okay, that's a cool idea. So this can take actions on its own. What about that?
Going back to broom, that joke is it's a cleaning agent.
Yeah, it's very good. I appreciate that a lot.
Can a fire take actions?
It does, doesn't it? Like it
does it?
Well, it turns things from wood into charcoal.
It's more like an obstacle, if anything. No.
Fire is an obstacle.
Well, like, because the fire, I mean, it does the same thing all the time.
Aha.
Yeah.
It does the same thing all the time, but they seem to be, like, it does move. Yeah, it's almost alive. Basically, it has a metabolism, you could almost say.
But it's like it doesn't make any decisions, so it does the same thing each time.
Perceive the environment, or you could perceive the environment and actuate and interact.
Yeah, that's right. It doesn't perceive the environment. Well, but at the same time, how does the fire know what it can burn or not? Like, it doesn't necessarily burn rock, but it burns wood. It doesn't burn water. It's almost as if it knows.
Well, I think fire doesn't receive any feedback from the environment it's interacting with.
Yeah. Yeah. I love this one because my biology teacher used to do that to me, and he used to try and convince us that fire was alive because it moves and it has a metabolism and it multiplies and stuff. And yeah, I can assure you fire is no more alive than viruses are. Okay, so what qualifies as an environment? What do you think? Like the environment, obviously, yeah, the one that we're destroying every day. But that certainly qualifies. What about space? Does that qualify? But nothing happens in space. Like if you're in space and there's nothing to bounce off of, there's barely any gravity. Does that count?
There are differences. You can actually get.
I really appreciate it, but we've got a whole bunch of other tables. Would someone else maybe volunteer to try and answer? I'm going to pick holes in you, whoever answers anyway. So, that's not helping. Just have a guess. What do you think? Why does or doesn't space qualify? Yeah, sorry. John, wasn't it? Yes.
Very good memory. Just in the context of what we're talking about, it seems like
Googling doesn't count.
Sorry.
No, sorry. It's sitting there with a laptop.
It seems like we came to the opinion. Well, let me just say this: that an agent is a being that takes actions and receives inputs from an environment. So it seems like if we want to define an environment in the context of what the action does, what the agent does in that environment, if space doesn't give you any inputs, then perhaps it couldn't be an environment for some agent.
So you think the environment depends on the agent?
For an agent, yeah, the environment is only meaningful in this context if it can interact with the agent.
Okay, that's an interesting point. So what about this then? Could a circuit, an electric circuit, be an environment?
Depends on the agent, I guess. Could be, maybe.
I'm going to make the argument that not only can a circuit make an awesome environment, the brain can make an awesome environment. Oh, good timing. Right. So what do you think qualifies as effects or feedback? Yeah?
A change to the environment?
A change to the environment. Okay. So you mean like the weather?
Well, that's not specifically what I mean, but that could be
Okay.
like, let's say, you take the action to push on table, the environment is changed by table movement.
Yeah, right. Yeah, I guess, you could look at it that way. That's true. So when you push on the table and it starts raining, that would not count.
As an effect?
Yeah.
Yeah, I guess that wouldn't be an effect.
How do you know?
Well, that's the kind of thing you have to learn.
Ah, very good. So I'm a lot darker than you are. You're much nicer than I am. That will be my first idea of an effect. Like if your agent dies, that's definitely feedback. Like that's sort of me. To me, that's the most primitive feedback that I can think of. Agent stops working, that's feedback. Yeah. What about finding treasure, money, riches. Yeah, reward. I mean, maybe that's reward to me, yeah, because I can spend it. But what if my Roomba comes across this? Yeah, my Roomba is going to complain because it's going to get all stuck with all the coins in it, and then I have to clean it. Yeah. So, and what about things like peace? Does that count?
If everything goes expected.
That's an interesting idea. So if everything goes expected, what do you mean by that? And could you grab the mic, wherever that is, to explore a bit what you're thinking?
Every time something is expected from an agent, like it will give something what we expect. So if we get the same thing, what it does, then peace. Like sometimes it malfunction or it doesn't do as we expect.
Okay. But I was thinking of it like, I made this slide before I heard the news. I was literally more thinking of it in terms of like world peace. Like, could world peace be a result, an effect of the environment that you could feed back into your agent?
I don't know. It could be.
Because if you can't, then the whole Skynet thing is kind of moot. Because what are we afraid of if we can't train a machine to make peace or war or whatever? Then there's really nothing to be worried about with
I think it's
artificial general intelligence.
I think it's contradictory because we can never know like until something like that happens. Like
Okay.
what if it doesn't bring peace to the world, or it yeah, what if sometimes the AI, I will tell, so as an AI it can.
Yeah, you made an interesting comment. What was it you said?
Some things are subjective.
Right. What does it mean for the agent that a thing is subjective?
I mean, what is peace?
Yeah. Okay. So what would it mean for your agent to yeah. So I totally expected this. Let's take 5 minutes to like just discuss and think about, because we want to do machine learning. We want to do shit with computers, sorry. We want to do beep with computers. We have to quantify this. We have to somehow put this into numbers. Yeah. So have a chat for 5 minutes, and feel free to get up, stretch your legs, jump around, and think about how you would quantify this. How would you quantify peace? How would you quantify death? How would you quantify riches? How would you quantify your environment? And why would the brain or circuitry be an environment? What could be? How could that work? And how could that work in numbers? What does that mean? And how does your agent relate to that? And how does your agent relate to those numbers? Because eventually your agent will also be numbers, right? When we want to do this in a machine, everything has to be ones and zeros at some point. So the only thing that makes sense is if we can translate this into actual number values. I'll see you in 5 minutes. Wow, we've got 7 viewers. That is really cool. And unfortunately, my system just told me that for some weird reason, it can't display any questions at the moment. So I have to find someone to view the chat in case there are any questions. I will get back to you.
Yes, I think the peace would be, I don't know, number of people died in a conflict.
I think it can be anything. The answer
Does that mean we need a scope? Once we have scope, then we probably know how to define something. Like what you said, it's a very objective.
Okay.
If no one's attacking you, you have good diplomatic means, getting started. If everything is, if you have good relations with everybody, you can quantify that as peace. Everyone has an interest. You have no conflict of interest with anyone. And that's a situation of peace. In some situations, peace is to be quantified.
All right. So I can see some really cool questions on YouTube already. It's awesome. Please feel free to have more discussions there while we're discussing what it means to quantify
Conflicts numbers.
the environment and the reactions of the environment for the agent. So yeah, and what I can see so far is fantastic. So I'm glad whatever is happening there. I have to intervene on screen.
You can go to the human body's chemicals. If someone is in a very high morale and then very excited, then some blood sugar rises, some biometric things now we can go from there to have it quantified.
You can sense if someone is feeling good, right? You can't quantify if someone is.
I think I would say that like
Happiness, that depends on what you call it.
Once you have a scope, so again, I think it's like what we said, make a scope, and then we can based on the scope, based on the grounding, and then we can make some definition. Once definition is there, quantify like what.
I think those things are quantifiable.
Yeah, once you find the correct metrics.
Because, yeah. Because like intuitively, like this is how people work. So if we want to have like a good meeting, for example, like a good atmosphere, then we will not say things that can be like offensive or controversial. Like somehow, and this is how we. Yeah, but you know, I think it's like some, you know, have you heard this like a phrase like reasonable person would do, or like again with good vibes. There's like I think everyone would reasonably understand what those good vibes. Yeah, sure, there'll be some.
But what about agents? Like we are not like we can be agents, but what about the agents? Do all the agents understand these things at minute basis?
I think probably like the majority, yes, probably they would. We always accept this. But I think yeah, I know it's like hard to like grasp what they are, but yeah, that's what I'm like getting at. So let's say you like again going back to date, don't have like a date with someone, and yeah, you're trying to react like adapt and react, trying to achieve the best outcome. It won't always be the same. The same practice will not always work. You will need to adapt to the other person. But I'm saying, it's like hard to intuitively quantify those things, but somehow you know what to do. Yeah. So what I'm trying to say is like we don't do those things explicitly. That there are no numbers like what's the conversation flow number or something, but you like know how to react.
Cool. Okay, so we've got some participants online as well, to whom I have to apologize again because unfortunately my the Mevo app that we're using to stream this is currently not able to display questions on my phone. So, but I've seen you've had some really amazing discussions online, and yes, most of what I've seen there was very interesting and also correct. So one of the interesting points that were made there was that the death of the agent is when the agent can no longer score. So it could literally be that it's not dead per se, but that it's caught in a loop. Yeah. So when the agent can no longer make any kind of progress, that could also count as a death. And you'll see eventually, when we go to some examples, that there are these what's called terminal states, out of which the agent no longer, can no longer escape, if you will, which are just the end of an episode. Right. So just to sum up where we were, we've got an agent which determines like who does it, and the manifestation of the agent in the environment is the action. So whether you're a smart light switch or whether you're a self-driving car with all sorts of different elements to your action, accelerating, braking, steering right, steering left, and so on, your environment is generally, that's the general terminology used in reinforcement learning, is the state. So the state can be defined through anything. The state can be defined by a whole bunch of voltages, for example, in a chip. The state can be defined in your brain as what you see. So coming back to the idea of space, yes, space can be your environment, but only if you are, say, for example, in a spaceship that is different to an airplane, because the way that your ship would react to your actions would be different to the way that an airplane reacts, and you wouldn't fly them the same. Like a lot of the, like, at least that was one of my gripes with Star Wars, a lot of the maneuvers that you see, the fighter planes and so on, or like the spaceships doing, are very airplane-like rather than spaceship-like. And so the environment itself is really dependent on where the agent is embedded in and what the agent gets as feedback. So the effect has to be the reward to the agent. And so especially in terms of the reward, what have you come up with as to how to quantify the idea of these three fundamentals? How would you express your agent and state system and reward in numbers? Oh. Anyone?
For which application? Like
for any an example. Feel free to give an example if the mic is somewhere.
Okay, so I guess a simple one could be like cars.
Mm-hmm.
So your agent is the driver. Actions it can take are what the car can do. Mm-hmm. So brake, go forward, turn, lights, that kind of stuff.
Yep.
Its state changes by where it is,
mm-hmm.
or like how fast it's accelerating, that kind of stuff.
So when you say its state changes by where it is, how is the state encapsulated in numbers? What would your agent?
So you could take a multitude of things depending on what you want to study.
Mm-hmm.
You could say your speed, your location.
Mm-hmm.
Let me think. There's a bunch of other things you could do. I can't think of any that quickly.
Yeah.
Yeah, good enough. And effects, it depends on what you're trying to accomplish. Like, is it a racing car?
Mm-hmm.
In that case, it could be like time elapsed and like distance traveled.
Yep.
How close you are to the goal.
Mm-hmm.
Or if...
so that already gives you some of the elements that you would need for your environment to be described, right? So you would need the time to be described. You would need the distance to your goal to be described, depending on your purpose.
Yeah, exactly.
Yeah.
Like I'm sure. I mean, there's maybe some other purposes that are less simply defined.
Mm-hmm.
Like I don't know, some kind of exploration vehicle or something.
Mm-hmm.
Maybe in that kind of case, you would look at area mapped. I don't know.
Yeah.
I'm kind of spitballing here.
Yeah, no, that's totally cool. Anyone else? Any ideas? Any other examples that you could think of?
Just to add to the driving one, would you set your environment every time you get into the car? So if you sort of program, I want to get from point A to certain point B.
That's a really super cool question, and we'll get back to that later. Keep that one in mind. Andrew, would you maybe describe your environment a little bit?
So I coded up.
If you could hand him the microphone, please.
Yeah. Thank you. Thanks for putting me on the spot.
So I coded up a environment based on a 1970s text game, which was basically called Chase, where you have an agent, you have 5 robots, and you have a electrified field that they are moving around. And so and it's just like normal text. So the agent is the player, has the actions of moving one of 8 directions or standing still. Each time they take an action, the state changes. So obviously the robots move towards the agent. And the reward is that every time that a robot goes into a zapper, is that the agent gets 1 point. And so for the agent to win, to maximise their reward, they'd get 5 points. So that's the way we broke it down.
Playing field, I think, was 20 by 20?
Yeah, 20 by 20 with 10 zappers randomly spread.
Yeah.
On the field, and then the robots dropped, and then the player dropped.
And in your encoding, you had, what was it? It was 3 channels.
What do you mean by 3 channels?
Was it a channel with a single channel with the player position, and then robot position, and then zapper position? Or
it was actually a matrix. It was like a 20 by 20 matrix.
Yep.
So you. To actually do something with it, you probably had to flatten it. Although somebody took Chris took a CNN approach, where he actually tried to he treated it like an image, and tried to look for features to determine what is the best action, which was interesting because I just did flatten it into one line. So there's different ways to approach it, but that's sort of when you come to what's the model underlying the decision making.
Yeah. So your agent was the player, and as soon as the agent moves, the environment changes with the robot moving or robots moving towards the player. So in the next complete image of the state, you would expect the robots to be closer to the agent. So,
which is like if you compare it with, say, simpler ones like this scenario called Frozen Lake, where the player moves, it's a 4 by 4 or a 16 by 16 square. I can't remember exactly. Yeah. And there are pits, and the pits never move. So in that case, the environment does not change in response to the player's action. So it's probably a simpler problem to solve.
Well, we'll get to something like that in just a little bit. So in principle, it all works like this. You've got your agent interacting with the environment, and the agent takes an action, and the thing that happens is that the state that the environment is in changes. So, also not the state that the environment is in, that the agent's state changes. So in case of the frozen lake, that could simply be the agent moves 1 step to the right. And if that is possible in this environment, then the agent is now 1 grid field further to the right. That is a new state. So in principle, if you had if you were just a really boring kind of like chess figure or on a checkers board, you have, if you're the only figure on the board, you have 64 states on the board that you can be, where you can be. So we want to define our state. So some of these are really useful and really good definitions for a state, and others might not necessarily be. So for example, in the case of our self-driving car, it might be useful to know whether you are on the road or whether you are on slippery ground. Yeah. But how to define that can be really, really hard. So you might be able to do that with an object detector, an object classifier, but there might be completely different methods to find out whether you're on the road or not. Maybe you have some kind of a detector. Maybe there are magnetic strips in the road that tell you this is the road. That's also possible. So you could detect a magnetic field. Yeah, that could also tell you where you are. The strength of the magnetic field could give you an indicator. And then your environment consists only of that. Your environment eventually only consists of these metrics. Yeah. If you're a submarine, the depth that you're at could be one of your metrics. The outside pressure could be one of your metrics. If you're a plane, the altitude that you're at could be one of those metrics. Yeah, the wind could be a metric. The current fuel gauge. Do you have fuel? Yeah. Well, your battery charge if you're an electric plane, or the fuel gauge of your plane. Yeah. If you're a racing car, the total weight of the car actually plays a huge role. So the weight of the entire vehicle could play a role. Yeah, your orientation with respect to the poles could play a role if you can measure these. So in all of these cases, your state and the reward is, maybe a bit philosophically, the reward is not necessarily part of the state, but because it somehow has to be measured, it has to be somehow detectable by your agent. So it somehow also has to be expressed, albeit implicitly, I guess, in form of a metric of some sort. So as we said before, you could have the distance traveled, the distance to your destination, and so on. All of these can be metrics. It could be a different metric to see what time it is, as opposed to how much time has elapsed. Yeah, it could, like, for example, if you're, in Adam's example, if you're one of those exploratory vehicles, yeah, you could measure how much time has elapsed in total, or you could measure how much time has elapsed before you declare a segment of your landscape, say, surveyed, and then move to the next one. And so to minimize the survey time per segment. But how many you measure doesn't really play a role, so how long you take in total doesn't. Or it could just simply be that you measure certain time steps, like literally, if you will, drops in an hourglass, and you get a negative reward for each of those time steps that have passed. If you then accumulate your rewards at the end, then the longer you've taken, yeah, the less you'll be left with. It's kind of like this. Yeah, energy goes down usually as you use your phone or whatever. So it's like a negative reward almost. So you can use that very, very well. So we've had a lot of thought about how to express this mathematically and how to express this in numbers. There is a formalism that's used to define a particular configuration, yeah, of the environment and the agent and so on, when you want to talk about decisions to be made and how to learn about decisions, and that's called a Markov decision process. And that's where your comment from before comes in. Yes, you would not have to reset the environment, but you would have to be independent of the environment. Yeah, the point about a Markov decision process is that the state that you're in has the Markov property. It doesn't matter whether you got here at 10 in the morning or at 10 at night, as long as you can make the same decision. Yeah, as long as it doesn't depend on whether you've been there at 10 in the morning when you get there at 10 at night. Yeah, the present has to be, the future has to be independent of the past given the present. So we define an MDP with 5 factors. So S is the state, that's this thing that we're in, and this can be, that's why it's bold here, that can be a vector. That can be a vector of factors. That could be like, the temperature of your tires, the angle of your steering wheel, the speed that you're at currently, the fuel gauge, or charge of your battery, and so on. The action from a pool of actions. So this is very important about your agent. That defines the agent in its reaction capability to the environment. So for example, if your agent is the spaceship that we spoke about before, and the agent has 4 thrusters and that's it, then there might be certain aspects of the state that the agent can't really do anything about. And the only actions that you can take could be fire thruster 1, 2, 3, or 4, or similar to moving on a grid, going up, down, left, right. Yeah, you might not be able to go diagonally. As we said before, in terms of the frozen lake example that Andrew spoke about, what's the probability of transition to a state S prime, i.e. just the next state from any state that you're in, given this action? So if in frozen lake, where there is a chance that the ground is so slippery, yeah, that you can't make it to the next grid point, or the ground is so slippery that you go too far, and you also can't get to the next grid point. Yeah, this gives you a probability of getting to the state that you were so to speak aiming for. Yeah, and the reward given the next in the next state, given the state that you started from and the action that you've taken, is the recording of the effect, as we spoke about before. Now, fifth factor that we haven't spoken about so far that's really important when you have finite and infinite segments that you want to distinguish is the discount factor. So it could be that your agent is just acting infinitely, and then you would never reach an endpoint from which you could say, okay, so let's just do the books and see how well we did. So you have a discount factor that gives you kind of like a horizon for which you evaluate your decisions. So let's investigate this Markov decision process. A Markov decision process this is an example that I stole from David Silver's excellent course on YouTube. Markov decision process in this case doesn't need to contain any specific actions. Here the transitions from one state to the other are random. So this is just a Markov chain. Yeah, a Markov decision process is just an extension of that where you actually make the decision and these turn into transition probabilities. Yeah. So from class 1, yeah, you have a 50% chance to go to Facebook. There's like no reward for that. Yeah. I think the rewards should be, yep, here they are. So it's negative reward for going on Facebook. Of course there is. And for arriving at class 1, you would get a negative 2 reward. So you transition from class 1 to class 2. Working in class is hard, so you would always get a negative for going from one class to the other. If the class is boring, then you fall asleep. There's no reward for going to sleep. And as you can see, there's no exit from here. So once you sleep, you have no further chance of scoring. And once you sleep, it's game over. You can't get out of this one. Similarly, when you make your way through all 3 classes, there's only one way out. Yeah, there's only one result that leads out of the pass itself. This is not a final state because after that you go to sleep. But once you're in the sleep mode, you can't go back and do anything else. Whereas if you end up in Facebook mode, there's a very high chance that you just you keep on scrolling and you accumulate these negative rewards, and there's a small chance that you get bored and go back to class. Similarly, once you've hit class 3, you've accumulated a certain amount of reward, and then you might want to go to the pub. And then from there, you can pop back into any class with a certain chance, and you have to start over again, which gives you more negative rewards. Yeah? But the pub itself gives no reward. So to iterate that again, the magical Markov property is, it doesn't matter. Yeah, let's say you're in class 2. It doesn't matter whether you've been in class 1 before or not. You can still make the same decisions from class 2 as before. Same with the pub. It doesn't matter if you've done this loop, yeah, like 3 times or 7 times. It will matter, of course, eventually with regards to your total reward, yes, but for the decision itself, whether you go back to class 1 or class 2, these values do not change regardless what you've done before. That's the important part. That's the Markov property. Was there a question with regards to that? Is there anything unclear? No. Okay, good. Yeah. Where'd the mic go? That might take a second.
Yeah, for the pub.
Yeah.
So where is it like the reward is 0 or not available?
I think I might just have been lazy and not added the reward here. The reward for the pub would be 0. Yes. So there's no further reward. It's the same as here, but this is a terminal state and this is not. Yeah.
So question about
Yeah.
this diagram. Are you assuming that the actions? So for the action from going from class 1 to class 2 has a probability of 1. So if you go into class, if you take the action to go to class 2, that you will end up in class 2 and not.
That's a good question. So in this case, it remains stochastic, similar to what we've talked about with frozen lake, where if you want to go to class 2 from class 1, the probability is not 1, the probability is 0.5. And there's a completely different discussion. I'm one of those people who are absolutely convinced that there's no such thing as free will. So for me that makes perfect sense. But the probability that you actually get to execute that action successfully, is 50%. That comes back to the probability, the transition probability factor in this 5-tuple about the Markov transition process. So we've got the state, we've got the action, we've got the transition probability, and the reward for the action. And the where the gamma factor comes in, and we'll have an example for that later as well. Give me 1 second. Is how, as we calculate back, as we look back as to what happened in this episode that we went through until you went to sleep, like at what point, like how long ago you did this. But it has no effect on the actual transition probabilities of the state. The question?
Yeah, I have a question. The Markov property you're mentioning here, is this property of this system, or is this an assumption? So I mean, broadly, I'm asking if this reinforcement learning can be used for any problem or for certain problems that have these characteristics.
So everything is a spherical cow in the vacuum. We're just assuming that that's totally true. That is a super important question. We are assuming for problems that we want to solve that way. It is required, but there are ways that you can try, like to look at systems. You can try and reformulate them and states or different Markov decision processes. So there might be ways to look at a problem that you cannot assume that they're Markov, but you might be able to expand your assumptions, or you might be able to use, for example, different observations, like you expand your state and say, okay, the time that I observe, or like, for example, if you think of Thompson sampling in a multi-arm banded situation, you can think of certain conditions that then become part of your state description. So usually, yes, you can assume that, but it can just become really expensive to make it so that you have this Markov property. But in principle, that's what we're assuming, yes. Adam, grab the.
Are we saying that there is only one action in this? Because it seems, say we're at class 1, it seems that there's a 50% chance we're either going to end up on Facebook or go to class 2. Not depending on if we take a different action or something.
That's a great observation. I cheated. When I stole this from Silva, he's literally only talking about the Markov chain itself, where there's no action decision. It would, of course, make no sense to say, I want to go to sleep, but I'm so excited about this course, and it can't be any other way, that I only have a 20% chance to go to sleep. No. But in terms of an actual Markov decision process that we're learning about in reinforcement learning, especially when it's a sort of a discrete state, kind of like this, then this is how it would be. Like your transition from this state to this state would be 20%, like your transition probability, if you took this action. If that was your, you would have which gives us +1, or we fall into the pit of doom, which gives us -1. And let's just talk about deterministic actions. There's just no chance that we're not succeeding in our action. We'll get to an example with some noisy action where it doesn't always succeed in stepping forward. The robot got a bit banged up, fell into the pit of doom one too many times. And let's just ignore this discount factor for now, as we're going on. How on earth? What did I? Oh, that's right. Now I'm a bit confused, but okay, cool. We look into how to deal with a situation like that in just the most minuscule and most simple way. These are the general ways that in reinforcement learning at the moment people are approaching reinforcement learning problems. There are some ways are dynamic programming deals with discrete problems like this, mostly exact solutions. Although for Q-learning, for example, you'll see that there are deep learning solutions. Policy optimization problems are more suited to continuous problems, especially continuous action problems. And there are some somewhat more esoteric or exotic and often closer to robotic optimal control problems like derivative-free optimizations, evolution problems, and natural evolution strategies, which are not necessarily your run-of-the-mill reinforcement learning that, for example, solved AlphaZero or is currently winning StarCraft. Like that. And the actor-critic methods, which are very, very popular, are sort of a mixture between dynamic programming and policy optimization. And right, so this is what we'll be looking at. And that's why I did it. Okay, cool. So to talk a proper mathematical way to evaluate your Markov decision problem, that's what you want at the end of your episode or the end of your action or the end of your agent's life. You want to have as high a reward as possible. Yeah, and the return is defined as the total reward over time. This doesn't necessarily mean wall time. This doesn't necessarily mean the time that your clock is counting. Yeah, this could be choose a value of 0.8 after a bunch of time steps. 0.8 raised to a certain power is close enough to 0. Yeah, not a spherical cow in a vacuum. But it'll become the reward after a certain point in time will become meaningless, and that's what your discount factor does. It kind of artificially terminates or artificially creates a horizon after which you don't have to worry about the reward anymore. Now, the state, any particular state that you can define, is just evaluated by what reward or what total return would you get starting from here. How good is it where you are? Kind of makes sense because the closer you are to your goal, yeah, the better. Which is kind of, it can be a bit difficult because it feels kind of like, well, the day before my graduation would be the best starting state for my education, because then I would have to be only at uni for one day. Would probably be very cheap, but of course you have to somehow get to that state. And in a way, the day before graduation, with all the knowledge that you've acquired, all the learning that you've done, which would of course define part of your state there, is the closest state to the goal, the closest state to the eventual reward that you want to get. Yeah. So there is a series of equations, and one in particular that's called the Bellman Equation, which combines the return, the definition of the return, with the value of a state, and this gives us the state value function. So for each state, we get an expectation value for its for the worth, if you will, of that state, and that is just simply given by the reward we get on the next time step plus the discounted value, because that's the sum of all the rewards, yeah, for the next state. So you get this telescopic function that tells you what a state is worth, and that makes it possible to use this function alone to evaluate a whole grid of values like we had in this example. So go to this one, and at the next time step you're here and you get rewarded with the diamond. Yippee! Yeah. Here at the next time step you go to this thing and there's nothing. So you don't get rewarded with anything. So the value, this reward here at t plus 1, yeah, is 0 for all of these fields. Whereas for the other one, it doesn't matter how long you stumble through this labyrinth, yeah, as long as you eventually get here, yeah, all of these fields are worth 1. And this idea is based on yeah, the final reward. So, and the question is, okay, so why not -1? Yeah, why is the reward positive? Any takers?
So you can have cost as negative.
Yeah, but you could do it the other way around.
I'm saying because reward's positive, so they're already having a positive number associated with a positive state.
Yeah, but why not make it all negative? Why not turn it all upside down?
So it's relative, I suppose, but I prefer to have it positive.
So that's your preference.
Sure.
Is that binding?
So that's sort of like a decay factor.
Could you where did the microphone go? Sorry, I should have handed the microphone over to John as well. Let's remember that. No, go ahead.
It wouldn't make sense if it's negative. It'll like alternate. Why do we prefer odd number of future those as opposed to even? Because it'll alternate at every. When there is even, it'll be positive, and then it'll be negative.
Okay. Each state, yeah, this is an example for a policy like we spoke about before. Each state has a distribution of actions that fully defines what to do. So the policy gives you an action given a state, yeah, and then hence the policy is given as the probability, and in this case here, this is a deterministic policy. We've got a policy that completely executes like deterministically, and there's just no stochastic element. If we want to go north, we will go north, yeah, and there is a method, there is a way to use this, yeah, to use. Could you pass the microphone over to John, please? So let's not have you miss out this time.
So I'm new to this, but I've watched 2 lectures online, I'm saying, about machine learning, I'm saying, and they talk about having the pi theta of the state function of the state, I'm saying, at time t+1, given the observation at time t and the action at time t. I'm saying this is a way, I suppose, to be able to discern, I suppose, what the state is given what's observed and the action, even though what's observed can be at times misleading, I'm saying, because you could perhaps have a photograph of say a cheetah or a tiger chasing a gazelle, then you have a car running in front of the cheetah or gazelle, the tiger, so you can't see the what's chasing the gazelle, but it's still being chased in actual academic process, I'm saying. And I guess I'm saying, I suppose, is that so I suppose I more would think it's wiser to infer the state given the action than to infer the action given the state.
Okay. Was there a question in there? I'm sorry.
So I suppose I was more saying that you've got the probability of the action given the state, but I think it would be more useful to have the probability of the state given the action.
But you have both, just not this state. You have the probability of the next state given the action in the transition probability. Because otherwise it's not a bijective function. So you don't have an action associated with a particular state. So you could maybe say, okay, I went left, so I could have been, I don't know, in Birmingham but it doesn't necessarily make sense to talk about this action having occurred because I was there, unless there are maybe some particular review functions that you might want to use to analyze some kind of frequency of actions or anything like that. But in terms of the decision making itself, it doesn't make sense to talk about the state as a result of the action when you're in the state. The only way that the policy makes sense is in terms of the transition probability to another state given your action. So what happens as the reaction to your action?
The state, I suppose, is created.
Yeah. Do you want to? Yes, the state. That's right. There's as we had before, like S prime, the next state, or like S at t plus 1. Yeah, here. Is created by that action, which is why we define the value of an action, or the value of an action given a certain policy pi, yeah, where you have the state action pair, like you're in state, let's say number 7, and you take action number 2, yeah, then you would expect the reward that comes out of that and added to the reward coming from the next action given the state action pair that you choose in the next one. That would be for like as the action values sort of chain up, similar to the state value functions from before. Yeah. So as we've seen in the diagram before, there's dynamic programming. That's the technique that's used to evaluate the policies and values, actions and states. So let's go to our example from before with our 11 states, 1 per grid square. If we have 11 states, yeah, and we have 4 different actions to choose from, that's already pretty crazy. From here, you've got 4 actions to choose from. Yeah, for every action that you can choose there, you've got another 4 actions to choose from, and so on and so on. The number of different deterministic policies is way too large to just simply, try and just ballpark, just find the best one after trying them out. So you want to go and improve them step by step and in a logical fashion. And the way to do that is policy evaluation. It's fairly simple. Yeah, assuming we have full knowledge of the MDP, and that's of course a totally cheatery assumption. Yeah, assuming we know full well the transition probabilities across every state, assuming we know all the rewards and so on, we know the extent of the MDP, we know the terminal states and so on. We can get the value for each state under a certain policy. And let's just take that policy from before, yeah, and evaluate that just to give us an example. Assuming we have our little robot in this field, this is field 1, 3, yeah, and we're following this deterministic policy, which is like, up, up, and right. Where this time we want to make sure that we are taking time and like the distance to our goal into account. We still have no rewards for steps that don't lead us to any reward. So we move forward, yeah, and we get a reward, and then we move another step, and we multiply the reward that we get there by 0.9, and then we take another step, and we move that multiply that reward, by 0.9 squared. In this case, that gives us that 0081, and that, yeah. I think I originally had intended for someone to come up here and solve that, but I'm not going to do that to you. That might be a bit daunting. But this is literally the way to do a policy evaluation on the policy pi here that we see on that little map there, which gives us a specific action to execute in every state. Yeah. The reason that there is that I did kind of cheat before, it's not 11 fields that we're looking at, because the action here is completely irrelevant and the action here is also completely irrelevant. It's only 4 to the 9, but it's still a ridiculously large number. So we have a decision already made for us with this policy, yeah, as to what to do in each state. And when we can follow that, we can evaluate what the state is worth based on this, if we do this, for each of the states, thanks to this formula. So how do we improve a policy? Well, clearly, next time someone asks you whether you're a god, you say, yes, that is policy improvement. Yeah. Last time he did it, last time someone asked him whether he was a god, it didn't work. said no. What we can do is we can evaluate all the states, then modify our policy, and then evaluate the states again. And eventually, yippee, we will get to not only the optimal value for each state, because we're acting optimally in each state, we'll always get to the optimal policy as well, because we will get to the values that tell us the best way to act. And so the way to do this is acting in a way that we call greedily. Greedy means just simply maximizing on your decision, like choosing the action that will get you the most future value or future reward. This is another point where the discount factor comes in, because if, let's say, you had a rather large maze like we had before, and there was only a sparse reward at the end, like only one diamond and only one pit of doom, and you have, let's say, 5,000 or so grid squares to get through until you get to the diamond. But let's say our discount factor is somewhere around 0.5. It doesn't take 5,000 steps for that thing to become ridiculously small. So no matter, but it will be really, really hard for your agent to evaluate what's a good action until they're really, really close to the actual reward. And it might just simply be that by randomly moving, you could with a random policy, you could just randomly move through this labyrinth or this grid until you find it. It could be that it's more like growing a plant than training a dog. Your dog has a much more efficient value or reward system, like this, just a single doggy treat and so on. Is much more. It's a much more direct version. Many agents. Yeah, John, you had a question. Can someone pass the microphone to John, please?
Sorry, very quick question. Does finite in this case just mean that there are no infinite loops?
I'm sorry,
does finite in this case for the MDP just mean no infinite loops?
The way to distinguish finite and infinite there is an infinite MDP could be something that just doesn't stop. Unfortunately, I don't have anything off the top of my head that would count as an infinite MDP, but a finite MDP would be something like your Roomba trying to clean the room before its battery runs out, and then it moves back to the charging station. And let's say that the end of the episode, that's what they're called, a single sort of gathering, a single round of gathering experience. The end of the episode could be either the Roomba running out of battery and sitting somewhere and you having to carry it back. That would be one end, and the other would be the Roomba coming back and charging back up. And you would just consider that an episode. But there could be, like we said before, the Roomba that is just continuously, or the exploratory agent. Let's say there's a solar-powered spaceship of some sort that doesn't require much power, so no matter how far away from the sun it is or any other star, it can always fly. That could be an infinite Markov decision process where it decides, like, which sector to map next, which quadrant, whatever. That could be an infinite Markov decision process. But you could easily turn it into a quasi-finite one by using an appropriate discount factor. And then you just look at some value, the usual epsilon. Epsilon always works. And then you say, okay, that's the episode. Right. And in a finite MDP, here we would say, okay, this is like in the case before, this is our diamond, like as soon as you hit the diamond. And it comes back to the very first example where we said either if we don't consider time when the reward factor, the discount factor is either 0 or 1, then we get a value factor of 1 or 0 for all of our cases. But if you don't do that, if you do this one step at a time, then you evaluate the reward that you got and then calculate the value of your state based on this and then reevaluate. the policy and change the policy accordingly. Because what we've done cheatingly with the example that we've calculated with the 0.9 is that we had a fixed policy. What we don't have here, is, let's say your little robot starts somewhere in your grid. What you don't have is a policy to make a decision. So, and that's why this is so cool, you can start with a random policy. And even if all the values in terms of your probability, if let's say you have an action that tells you randomly go into any of the 4 directions and you have a transition probability of 1, this sum eventually, thanks to the values that you accumulate over your states, will still give you the appropriate map of values for your state values. Does that make sense? That sounded a bit confusing even to me. Have I lost 99% of you? Okay, I'll carry on, hoping that this will become a bit more clear with the next example. This I've shamelessly stolen this from the amazing Peter Abel again. So we've got our example here, and let's say we've run around our maze once and we found the value of the diamond there. So with one round of value iteration, with one iteration of the diamonds there, everything else is 0, we get this. That's the minimum that you need to do anything, right? In this case, just as a caveat, they've added, in their calculation, they've added some noise. I meant to do one myself, I just ran out of time to do the graphics and stuff. They've added some noise, so their transition probability is only 0.8. But all that does, yes, Andrew?
So, quick question.
Yeah.
Wouldn't there need to be 2 iterations because there's 2 terminal states?
That's a very good question. Yes. You'd want your agent to die once. Yes, that's true. Maybe that's what they meant when they said V2 instead of K1. I don't know how it found out that there was a pit of doom after it found out where the sapphire was. Peter, if you're watching, send me an email. Right, but the pit of doom is we literally only need to know about the pit of doom once. As we're going through, we're just using this, and our probabilities and the rewards and so on to figure out the values of the fields here. So if you do the calculations, it's fairly straightforward. You've got a discount factor of 0.9, and a probability of 0.8. You multiply those, that gives you the value of this state. You've got an 80% chance of getting to the reward in the next time step after, which gives you a factor of 0.9, and you've got your 0.72. And in a similar way, with the same transition probabilities and so on, because they don't change. Nature is a total asshole. In real life, this can be different all over the map, right? But it doesn't have to be. So in this case, we're only talking about uniform noise and uniform transition probabilities. I'm sorry, nature. And these values just multiply. The interesting factor here is that given this, we can already see the pit of doom. It's better to be here, or better to be here, if you will, than to be here. You can't get away from this guy, and here you die. So here, this doesn't matter, and this way you're closer to the prize. So even after only 3 iterations, you can already see the value function for each state reflecting how good it is to be in a certain position. And so as you continue, if you do this for eventually 100, 100 is good enough. That's practically infinite, right? It doesn't change anymore. It doesn't change much after even 7 iterations to 100. The difference isn't all that great. But you can see here that now these 2 positions are actually equivalent. This one because it's further away, and this one because of the pit of doom. But if you look at this, yeah, it is still better. Like if you were here, you'd be better off going by this. You'd be better off taking the long way around because it's safer. Yeah. Whereas if you start here and you go here, it's interesting to see that our evaluation shows us that taking this shortcut is better than this extra step here. Yeah. This is just given that our discount value, i.e. our consideration of time, is so generous. If the discount factor was lower, those numbers would be different. Yeah. So you can turn this into a generalized policy iteration. The GPI does that one step after another. Yeah. So you could, for example, use this to change your policy after each iteration. Let's just go back to this one. Yeah. And you could say, okay, I've got my states numbered. I know what they are, and I'm still doing random everywhere except for that one, and that one, and that one. Yeah. I do random here because I don't know enough. Yeah. And here I go that way, and here I go that way, deterministically. And then as this changes, you change your policy, and you change your policy, and you change your policy. This leads to the value function for the states that you're looking at, of course, converging even faster. Yeah? Every time you change the policy to a greedy policy after a single evaluation, yeah, you get closer and closer and closer to the states. Because as soon as you drop your random exploration policy for all those unknown states, because you want to go to a particular next state, yeah, the value that's calculated for the surrounding states, of course, ramps up. So we've got what's called the Bellman optimality equations. Yeah, it's literally just do what's best. You just pick the optimal state value is given by the max action, the maximum value for the action that gives you the highest sum. Yeah, given all your probabilities, your action probabilities, and so on. Discounted value of the optimal value of the next state. Yeah. So for action values, it's the same thing. Your state action pair solved it. That's it. We've done reinforcement learning. Yeah, not quite. Nature's not like that. That shit's not like that. That's just, all of that is just pure theory. Yeah, this was all spherical car in a vacuum. When you have you're doing a self-driving car, right? Yeah. The only discrete thing I think about that car might be what gear you're in, right? Or whether your indicator is on or not. But other than that, the position on the street is continuous. Like the speed of the car is continuous. The angle of your steering wheel might be continuous. Yeah. Yeah. Exactly. Yeah. So, okay. Whether it's raining or not, whether you need to turn on the window, whatever, that might be something that you could decide. But what about that car? Is it a finite or an infinite process? Would you consider it an infinite process if you're doing a simulator where you're never running out of fuel? Yeah. So, for example, you could have a real car. Yeah. Right. Yeah. So that could be one of the factors that come into the car's state. But you could, for example, try a simulation first, where you don't have a battery to start with, right? And then you see what you have to deal with in terms of a state formulation, and then cut out all the bits that you don't have to worry about yet. Yeah. And how well do you know your agent? Like, for example, limited action space. Yeah. With the wheels of the car, for example, like how far does this thing actually turn? Yeah. How like to what degree do the wheels turn? That sort of thing. Are there things that you might not know about your agent? It could be, for example, that you know that you could turn the wheel right or left, the steering wheel, but you don't know how far. There could be that you what's another action that could be like that? Yeah, but that's not necessarily an action. That is something that you would want to define a reward function for, right? But you would, for example, you don't know the resolution of the camera, for example. That could be one thing. That could be something that determines how you want to model your agent with regards to that. If you have a high resolution camera It could very well be that you could use color. But if all you have is like an infrared sensor, that would be a completely different kettle of fish. And then whether your action space is discrete or continuous would make a huge difference. And that's what brings us to the algorithms. Like I said, we've literally just scratched the surface of what you can do with reinforcement learning. It was meant to be an introductory thing. This gives you a small overview. I've gotten this from, unfortunately, sorry, OpenAI, I forgot to put the credit there. There's an amazing resource on OpenAI called Spinning Up. Look it up. It's got code examples. It's got explanations for just about anything that you might want to do in AI. But it's also at a really, really great and high and deep level. So some of it might require a bit of Python experience, a bit of deep learning experience, and might be fairly advanced. Yeah, but some of it might be good to practice with to kick off. So, for example, if you want to look into Q-learning and deep Q-learning is based directly on the value iteration stuff that we just spoke about. So the algorithms in principle, as you see here, they distinguish model-based methods and model-free methods, where a model-based algorithm creates some kind of model for the world that has an influence on its prediction. Yeah? A model-free method, my colleague Fiona said, just suck it and see. They both can work fairly well. It doesn't mean that a model-based method is safer or better. It could, like both versions can apply to various problems. There's nothing that's better or worse for certain things. There's just considerations around, for example, when you have you wanted to not just make a self-driving car, but for example, a self-driving or self-flying helicopter. You'd want to make a model-based simulator to start with, because helicopters are expensive. So these are considerations that you have to make around the way that you solve your problem when you do this. There are two different ways of learning. One is called on policy, the other is called off policy. I'm just more going through this as a glossary to introduce some more terminology to you when you go deeper into this. I've got some recommendations as to where to start as well later on. On policy means that you're not changing your mind as to what you do when you move through the world. So you've got the policy that you're working with is the same as the policy that you're changing. Off policy could be like, as long as you're playing around, as long as you're learning, you do anything. You just do it randomly. Yeah. But then when it comes to deploying the agent, you have derived a policy that is the actual policy that is used to make the decisions, that is not this random policy. Yeah. So you have a completely different policy to what you actually made the learning decisions with, that is evaluating the state values that you got out of your exploration. Yeah. Two very, very important dynamic programming methods, temporal difference methods and Monte Carlo methods. They're related in a way. Temporal difference is similar to, they're kind of similar to on policy and off policy, if you will. Temporal difference methods update during your learning. They kind of change as you go. There's a very famous one, it's called SARSA, which, as you can imagine, stands for state, action, reward, state, action. That's literally what happens. Like, you have a chain of events and you update as you go, and then your policy changes. And because you could encounter the same state multiple times, like if you're this robot that's just meandering through your maze, then you might know better next time, that you might have seen this corner before, that sort of thing. Monte Carlo methods, Monte Carlo has a bad name. It's really just a mean word for gambling. It just means that you're sampling randomly. The only thing that Monte Carlo means is that there's randomness involved. And there are two key differences in Monte Carlo methods, one being first visit methods, where as you're going through your episodes and as you're sampling, you either count only one visit or you count all the visits. And then for temporal difference methods, you update your values in set intervals. So you don't necessarily have to take a single step and then update it. You could do it in like 5 steps and then update across that. This is similar to what you do with a discount value, where you give yourself a finite horizon. Yeah. If you have as you've seen before, if you have a grid world, if you have a finite environment like that and it's discrete, they're very fast. It's very easy to just record all those values in tables, update the tables, read from a table, and you're done. That might not work necessarily for continuous or stochastic policies. This is one of the algorithms. This is all there's to it. That's all that's to Q-learning. If you code this, you've got yourselves an agent. Might not be able to do much, might just be able to do a grid world, and it might take a while to learn. But if you want to make it a little bigger, you can play Doom with it. You can play video games with it. Deep Q-learning has been used successfully to play video games. Sarsa is kind of the same thing. It's just Sarsa is just the case where it's a special case of off-policy learning, if you will, where the policy is just always the same as the learning policy. So deep Q-learning, double Q-learning, they're all variations on this that use deep neural networks. And model-based reinforcement learning has a variety of options. I don't know very much about model-based reinforcement learning. We've done a bunch of these things in the book club recently because we wanted to know more about it. And there is a series of videos by Andrew Ng which discusses this in detail. The policy-based stuff that we've spoken about before is good when you can't deterministically be greedy about something, but you want, like for example, if you had a continuous action space and you don't want to know whether you accelerate or decelerate, but you want a definite value of like what angle should my steering wheel be at, what voltage should my electric motor be at, for example, like what voltage should I put this actuator on, what pressure should I give onto my hydraulics, and so on. Yeah, and they can learn stochastic policies and deal very well with continuous spaces. So I've got 2 hints for you where to start with all of this. If you want to experiment with reinforcement learning, go to gym.openai.com. It's a fantastic resource. It's absolutely amazing. Andrew, who just left, has written some for it. Other members of the book club have written material for it. I'm standing up here and talking. I haven't done anything for it, unfortunately. I'm just a benefactor of the amazing work that the people I know have done. But I just like talking, so I get to do this. And the other amazing resource that I can recommend is, and Thomas, if you're watching, that smile is so smug. I have no idea why you chose that picture. I've got that from his GitHub page, from his webpage. Thomas Simonini's course is amazing. It's great fun because he's got video solutions for everything. He's got solutions, notebooks for everything, and then everything is explained in really simple, really intuitive, and like long form, really, really well. And you get to try everything yourself, and you can look up, like basically you can scroll through the exercises and try to do them yourself, and if you get stuck, you can look up his solution. It's fantastic. And just to recap, what have we gone through? Well, we've gone through what's RL. It's a third type of machine learning. It's decision engineering. We've gone through the fundamentals of agents and environments. This is basically in principle, this is all that happens in RL. This is the most important thing. Yeah? In terms of metrics, you need to know about generalized policy iteration. This is a fundamental idea that as you know more, you decide differently, and then you upgrade what you do, you upgrade what you know, you upgrade what you do, and so on. And eventually, like the best state, or the best set of, not the best state, that's already taken, but like the best situation that you can be in is that you know the optimal state values, and that you therefore know the optimal action values, regardless of what the transition probabilities might be. This still holds for stochastic policies, and your policy therefore is just simply the one that gives you the highest likely reward. And in terms of algorithms, this is, like I said, just it's not scratching the surface. That's it's more than that. But this is one way of looking at the world in reinforcement learning. That brings us to the end. It was a bit of a tour de force, so thanks for sticking out. So you've already asked, and thanks for that. You've already asked questions throughout the session. Did you have any more questions with regards to reinforcement learning? Yeah.
Can we download this?
Yes. I will put a PDF with the slides onto the Meetup page, and I'll see if I can put them somewhere else as well. Yeah. Anything else?
Curious about the company. What do you do with AI in reinforcement learning?
Oh, okay. That's a brilliant question because we don't do anything with reinforcement learning. Like, I'm just the crazy person that loves reinforcement learning and think it's the fastest way to bring about the reign of our robot overlords. I didn't say that. No, I just really like it. I think it's fascinating because it's one of those things where when I learned that Google had reduced their the electricity bill for their air conditioning in their servers, for their main server stations by about 60% using reinforcement learning, I thought, whoa, it's not just robots, it's not just self-driving cars. This is actually really, really cool. And the thing about machines is that they can react so much faster than we can. They have this like really narrow focus, yeah. I think at the moment, at least, I can enjoy music, which a machine cannot. I can make music and I can groove with people and stuff, and I can dance and not very good. I can do these sorts of things that machines cannot, but there are things that machines are much, much better at than I am. Yeah. So if my wife has problems with a possum in our garden. Yeah. And if I were to install a machine that would just shoot a laser, even if it's just a really harmless, like sort of BB gun laser that just sort of burns the possum a little and just, discourages it to gnaw our figs and whatnot, I wouldn't wait there all night with a little laser gun. I'm a shit shot, and I'll probably fall.
I have a laser in my garden, and it doesn't distract the possum. They still come.
Okay, well, okay, maybe, yeah, don't know, but that's almost a relief. I don't know, maybe it just shoots the neighbor's cat instead. I don't know, but that sort of thing, right? Or I hope that one day the self-driving cars that the guys in the back there are currently working on, that will drive better and save lives in the sense that it will prevent people having accidents in the first place, and maybe also driving a bit more efficiently than me. Like, half the time I'm talking to my wife or doing something else or listening to an audiobook or something, yeah, and then I'm just driving too fast, or I'm just actually I'm one of those people who goes 45 in a 60 zone because I'm just absolutely fascinated by whatever Max Tegmark has to tell me or something, yeah, and machines don't do that. So a colleague of mine, Grace, she's phrased this really amazingly. She said, don't be angry that a computer is taking your job. Yeah? Be angry that a computer still isn't doing what you don't want to do. Yeah, and that's how I think about reinforcement learning. I feel like reinforcement learning is one of those areas where we can make a really great forage into things that are that feel like, at the moment at least, we still have to almost force people to do it. Yeah, I'm not saying we need to replace all garbage men. Like, if people want to do that, by all means, that's great. And I'm also not sure that reinforcement learning might be required for that. But things like that, we don't have enough, like clearly in Australia, we don't have enough fireys, right? So if you had, and those situations are really, really tough to judge, and you can't just make a machine that acts simply algorithmically, that simply just rolls forward, raises hose and yeah, you have to be really smart about this. It's not easy. And so to have a machine that could actually assist our firefighters, that would be amazing. Yeah, mostly because they're probably cheaper and more expendable, yeah, than your average firefighter squad or whatever other machine you might have. Yeah, to be able to scout something, to be able to have. Imagine you had a little firefighter on chains or wheels or something that could scout things where humans can't go and give information to people who really, really need to know this, or even make predictions and then tell people about what they think. The equivalence of, I guess, an active person, an active scout that can judge how dangerous the situation is for them, and the radiology expert AI that we're looking at right now, that sort of thing. And I think that could be incredibly valuable. What if we could one day replace pilots? I mean, airplanes are still incredibly safe, so I'm not sure whether pilots need to be replaced. But I wonder what that means for the pilots and their families. Like, they're pretty far away a lot of the time, that sort of thing. I don't know, maybe they don't want to go home. Sorry, pilots. But yeah, there are all of these jobs that machines could do for us, and we could just do something else. Who knows whether some of those pilots would make great painters or great musicians, yeah. And then we might see them on Patreon once we've replaced them, and some of them might be even more successful than Sting. Who knows? That's maybe that's a bit too optimistic. Maybe that's not taking the economic situation seriously enough. I would imagine it's probably a lot more difficult than that. But the other side of the coin is, what if there are jobs similar to a lot of the data and IT jobs that have come about in the last 10, 15 years? What if there are jobs that we don't know about yet that only a machine can do? Yeah. Because what other than a job, in principle, only that we don't pay our digital slaves, is that if we have a machine, say, algorithmically trading, yeah? And what if there are a whole bunch of jobs that we haven't thought about yet that will come into existence because we develop better reinforcement learning agents? Yeah, that would be very interesting.
But don't you think that humans will always be required to design those agents first and maintain them and
yeah. I don't think always. So I'm not 100% convinced that Skynet is around the corner. It feels, in fact, like the longer I work in this kind of field, that Skynet is actually further away than many people think. I think I would be very surprised if we, I don't like the word Skynet anyway, but if we had a fully functional AGI in the next 10 to 20 years, that would be a great surprise, I think. Not saying it couldn't happen, it totally could, but I must admit I'm more with Daniel Dennett on concerns regarding AI, and that is that we might not take your comment seriously enough and not use enough humans in design. When it comes, for example, to fairness in AI, when it comes to trying to have a broad consideration of political, philosophical, ethical, social, and so on implications. We're not talking to enough subject matter experts and that sort of thing. When we rely too much on algorithms and machines for decisions. So I would be as happy as I am to do stuff around reinforcement learning. I'd be very, very skeptical to let a machine like that do something that is influential on a huge scale, because it's really hard. It's really hard to judge the consequences, yeah, across such a broad spectrum. And even amongst us humans, it's really, really difficult. And then you have the scientific community, when they reach a certain consensus, that is a really powerful thing, yeah. So to expect the same accuracy from a machine is something that we dream about, but I think is actually really, really difficult. So I think eventually we'll get there on a long-term scale, yes. But I'd be worried if we didn't use people for design, yeah, for a long time, yeah. Anyone else? Anything? Cool. In that case, thank you all. I'll turn the music back on, have another beer, and yeah, I hope to see as many as possible of you next week. All of you, of course. Yeah. Thanks, Internet, and yeah, see you again soon.